the positions of the point P, A, and B, whereby AB is a vector itself, such that the column vector is written as 4, 1. We want to express PB as a column vector. So if you would like to, you may want to actually connect the 2 points together so that you could visualize it clearly. That PB is this vector because you have to start from P going to B. So with that, it will mean that PB as a column vector. How do we express it as a column vector? Amanda? 3 and negative 2. Great. Okay. Next, we look at part 2, whereby it says Q is a point such that ABQP is a parallelogram. Something that we need to be aware of, which I'm sure many of you will be, just a reminder, that when we are given a notation, or rather a name, okay, for a quadrilateral like this, okay, it will always be either in the clockwise sequence or anti-clockwise sequence. So we see that AB is already here. Okay, for it to be a parallelogram, it has to be somewhere on top here, such that it goes to P. It cannot be A, B, P, then after that Q over here, because otherwise the naming is not consistent anymore. Okay, so our understanding of parallelogram is that there must be parallel lines. Okay, so that means that P to Q will have to be parallel to A and B, while B to Q must be parallel to AP. So from the diagram itself, we are then able to locate where Q is going to be. And looking at the vector AP, we see that we move right 1 time and then move up 3 times. So same thing from B, move right 1 time, move up 3 times. So we see that Q will be here, because AP must be parallel to BQ. Okay, so therefore our BQ, okay, will actually be the column vector 1, 4. Okay, sorry, not 1, 4, 1, 3. Okay, in fact, you may not want to actually locate where the Q is, but just by understanding that AP must be parallel to BQ, okay, you will know that BQ will have to have the same vector as AP. Next, ABPR, in this case, is a parallelogram as well. So based on what I shared earlier, ABPR must be around here. So could you locate where R is, okay, or figure out what is the vector PR going to be? Okay, try to figure it out on your own. Okay. Hope you managed to locate it. Joseph, what is the vector PR going to be? Negative 4, negative 1. So all of us are able to get it. R is actually supposed to be here. Okay. Then in part 4, you are asked, do the vectors PQ and PR have the same magnitude? Okay. So PQ is this one here, PR is here. We notice that because ABPR is a parallelogram, that means the line AB must be the same length as the line RP. Likewise, ABQP is a parallelogram, so AB must be the same length as PQ. So therefore, PQ and PR must actually be of the same length. Okay, they have the same magnitude. Okay, so yes, they have the same magnitude. it is clear to us that PQ does not equals to PR, okay, because PQ itself, okay, is in a direction going in this manner, while PR is a vector whose direction is going in this manner. For two vectors to be equal, not only do they have to share the same magnitude, they must also share the same direction. Okay, so no, PQ does not equal to PR, since they do not have the same direction. Moving on to page 7. Okay, we are asked to draw in the grid provided, okay, these two vectors over here, which is not fully given to us. We are given, it is given to us in words, okay. But before that, I need you to actually just indicate some markings onto this grid first, okay, so that we can do some. We know quite what the sizes of the box are, okay. We wouldn't want to choose one small square as one unit, otherwise you have a lot to count. Okay, so we will need this scale over here. So every 5 small squares is 1 unit. Okay, so how I go about choosing this scale over here is because we could go and calculate what 2 times of 5 negative 3 is going to be first. So 2 times of 5 negative 3, just like how you do your scalar multiplication in matrices, we will get 10 and negative 6. So in the x direction, I need minimally 10. Okay. In the y direction, I need 6. I do not need the negative values in the y component. While for part B, 3 times of the negative of negative 4, 3. That means negative 3 times negative 4 and 3. So we will get 12 and negative 9. Okay, so with these vectors, could you try to figure out how these vectors are going to be drawn on this grid, okay, without them overlapping each other? So draw them with some space apart. Okay, make sure you got sufficient space. So please draw them now onto this grid. You may need to plan out such that you can have 2 vectors on the same grid without overlapping each other. Okay, so your two vectors should somewhat look like that. Okay, your start point and your end point may not be the same as mine. Okay, but for part A, it should be 10 medium squares to the right, 6 squares down. Then for part B, 12 medium squares to the right, 9 squares down. So your arrow direction should be pointing in this manner. Okay. Alright, shall we move on? Okay, next we're going to talk about addition of vectors. Okay, so how addition of vectors is going to work. Alright, relies on something similar probably to our matrix multiplication, where the number of columns, okay, and number of rows have to be equal for the left matrix and the right matrix respectively. Alright, so in this case, if I have the vector PQ and I want to add it to the vector QR, okay, it is going to create another new vector called PR. So we have to ensure that the two vectors here, okay, these 2 points over here, they are equal. Alright, then we can have a resultant vector of PR. Okay, but of course this only works if it's in this notation. Sometimes maybe we use this notation, okay, then it will just be A plus B equals to C, for example. Alright, it could always be D plus E equals to F, right? Any letters. Okay, so this one doesn't have any effect at all. But this will become very helpful when we do more vector questions later on. Right? So something to note about the resultant vector that comes out of two vectors adding to each other is that this PR is what we call a resultant vector. Okay? And in drawing, we usually draw it with a double arrow, okay, to indicate that it is actually a result of PQ adding with QR, and then we get this resultant vector PR. Okay? Sorry, is there an error in my diagram? Just realized PQ plus QR. Oh here. Sorry, I have an error in my arrows here. Then realize it should be double arrow like that. P to R, right? Okay, sorry about the printing error. Next, okay, we need to learn how to draw resultant vectors. For the physics students, you all draw resultant vectors in physics. You all learn that, right? Okay, so it's the same way, right? No difference. Okay. So given two vectors A and B as shown below, draw the sum of the two vectors A and B. So one way is by the triangle law. Okay, so we draw the first vector A first. So you may want to use a pencil in case you draw wrongly. So this is 2 to the right, 3 up. So I can start with any point. Let's say here, 2 to the right and 3 up. Okay, so this is the vector A. And then for the vector B, it is 4 to the right, 5 down. So I can from here 4 to the right, 5 down. And my vector B ends here. Okay. So in the triangle law of the vector addition, okay, it simply tells us that the starting point of A, okay, will be the starting point of the resultant vector. And then from the ending point of A, right, we continue to draw our vector B. Okay, we cannot draw our vector B elsewhere, so we continue it from the end point of A. Then after that, the end point of B is the end point of the resultant vector. So our resultant vector is going to look like this. Okay, double arrow. A plus B. Yep. Why that direction? Why not this direction? Well, then what are you thinking about? the other way. Why would you want the other way then? Okay, because we are starting from here one. Vector A, we start from here first. Then after that, we continue to have our A ending here. Then after that, B continues from where A ends. Okay. So you think of it like you're walking on a path. Okay. Or let's say from on the parade square itself, you can walk from the school gate all the way to this central staircase by taking a diagonal path, right? But you choose, there's another path which is from the school gate, you walk to the smart room, then smart room you walk across the set 1 classroom to reach this staircase. You understand? So it is the same path, right? So start point to end point. So this is your smart room to your central staircase here. And then this is the diagonal one cutting across the parade square. You understand? So yeah, this is the only direction that you can have. Yeah. So if it starts here, it must end here. Okay. Another rule, another law that we could also use to apply, okay, instead of the triangle law, we can do the parallelogram law. Okay. Although the triangle law already works very well. Okay. So what if, let's say, with our vector A, which is a 2, 3 vector. So if I start from here, 2 and 3 up, get this. Okay. What if my vector B, I refuse to start from this endpoint of A, and I have it here. Okay. So that means that my vector B is a 4, -5. So 4 to the right, 5 down. So what if my vector B is in this manner? Okay. Then we make use of the parallelogram law or vector addition, where it means that, okay, I can draw a parallel vector to A going to where B, the other side of B is. Okay. So when we use the parallelogram law, usually we do a dotted line. Okay, so we likewise do 2 and 3. So 2 and 3 up here. We use a dotted line. Okay. And then after that, for the vector B, we also draw a parallel one. Okay. So this is the vector B that's parallel, and this is the vector A that's parallel. So in the parallelogram law, it tells us that where it splits open, if you notice this starting point here, where the two vectors are diverging. You all know what the meaning of diverging and converging, right? Where it diverges, okay, is the start point of the resultant vector. Where the two vectors converge here will be the end point of the resultant vector. So your resultant vector will be this one here. Okay. So this is the start point of your resultant and end point of resultant. Okay. The parallelogram law is consistent with the triangle law, because if you notice that when I did my parallel vector to B, right? Okay, when I put it upwards, okay, this triangle is the same as what we had in part I, okay, when I use my triangle law. Okay, so they are consistent laws. Now next, from the two drawings, suppose vector A is this and vector B is this. So we see that A plus B itself, okay, the resultant vector is actually going down by 2 units, going to the right by 6 units. Okay, so our resultant vector here is right towards 6 units, downwards 2 units, so negative 2. Okay? And that is also consistent with the calculation of how we do matrices, whereby if I take 2, 3 and 4, negative 5, I add them up together, I do get 6, negative 2. Okay? So this is if you know the column vector, okay, of each vector itself. It is not all the time that we know the column vector. Okay? Next, example 6. The diagram shows a quadrilateral PQRS. We want to simplify these notations. So looking at part I, PQ plus QR, PQ is here, QR is here. So it's the addition of these two vectors. If I simplify it, it's as good as saying PR as the resultant. Even without the diagram, you should also know this answer, because so long as the middle is the same, the start point will be P, end point will be R. Okay, next for SR plus PS, okay, for SR plus PS, right, okay, SR is in this direction, PS is in this direction, okay, we could actually shift the notation around. Okay, such that I write it as PS plus SR, and then I get PR. Then in part 3, for PR plus RS plus SQ, okay, if I have 3 vectors to add, even if without the diagram, if I were to ignore it, okay, PR plus RS will give me PS. Then I have to add up with SQ. PS plus SQ will end up giving me PQ. Okay, so when it comes to vectors, in this case, don't fixate yourself over the location of the vector itself. These vectors are free to move around. Okay, the vector itself is just a line, okay, with a certain direction. So for instance, when we did SR and PS, right, although SR is here and PS is here, we can always just shift it, okay, up and down, right, such that we can do our triangle law and our parallelogram law as well. Okay. Moving on. Magnitude of a resultant vector. Okay. So to see the magnitude of the resultant vector, let's take a look at the magnitude of A itself. Okay. Since we have learned that the magnitude of a vector can be applied using our Pythagoras theorem, so 2 squared plus 3 squared, we see that magnitude of A is square root 13. While the magnitude of B is 4 plus negative 5 squared, 4 squared plus negative 5 squared, and we get square root of 41. So it does seem as though, okay, if we think of adding the magnitudes of A plus B, the magnitude of A plus magnitude of B, we are getting square root 13 plus square root 41. And that gives us about 10.008. We want to know, okay, whether the magnitude of the resultant, A plus B, is it going to be the same? Okay, so A plus B itself, using the column vectors, we see that it is equals to 6, negative 2. So by the same formula, 6 squared plus negative 2 squared is actually square root 40. Okay, and that is square root 40 is about 6.3245. So they are not equal. Okay, so we have to keep that in mind, that the magnitude of the resultant vector is not the sum of the individual magnitudes. Okay. Just like how we have one by one matrices whereby we insist on having the brackets, we have such a thing called a zero vector itself. Okay, when it comes to writing a zero vector, we use a bold zero, okay, which is written as a zero with a curly sign at the bottom. Yes. Yep, Joseph.
People mistake for zero as bold.
Sorry, I can't hear you.
Will they mistake a zero for bold?
Sorry, let me get to that for in a moment. Okay, when we want to represent the zero vector, right? Okay, if we mean the vector, okay, we have to write it in this manner. Okay, you cannot write a normal zero because a normal zero is a scalar number. Okay, so there is a difference when you're trying to mean the zero vector and the scalar zero. Okay, so what exactly is a zero vector? Okay, for instance, right, when you consider a person, okay, walking in a straight line from the front of the classroom to the back of the classroom. This journey, if I call it PR, okay, and then the person from the back walk back to the front, okay, that will be the vector RP. So because from the front to the back and then he came back to the front again, okay, he's back to the starting point. So the resultant vector, okay, start point, end point are both the same, it will be a zero vector. Okay, so therefore, PR plus RP, it will be a zero vector. You cannot write it as PP, it doesn't make sense. Okay, likewise, RP plus PR, it is also not RR, okay, it is a zero vector. Alright, and when you know that you're adding out vectors, the resultant must be a vector itself. It cannot be a zero value number. Okay, so there is that difference between vector and scalar. Alright? So therefore, when it comes to part A, when I want to simplify 8, -1 and -8, 1, okay, just like how we do matrices, 8 and -1 will be 0, -1 and 1 is 0. So this is another way that we represent a zero vector, but in the column vector manner. Okay, so this is a zero vector in a column vector form. Right? And to complete this itself, this vector equation, we know that a zero pair is formed with -6 and then the other one must be a 6. And to have a 7, I need a -7 to add up with that, give us a 0. Okay. So now that we have understood the addition of vectors, let's look at difference in vectors. So the diagram shows two vectors R and S. Okay, and for the vector R and S, right, we can use our triangle law as well, okay, to draw. So if you want to draw the vector R minus S, okay, do realize that R minus S is as good as thinking of R plus my -S. Okay, because just like in our algebra, okay, when we have plus and minus, it simplifies to a minus. Okay, so to draw out the vector, let's say if I were to start with a point here, okay, sorry, let me change my point now. with plus space. Let me start with a point here. Okay, so if I were to start with R is a 3 and 5 vector. Okay, 3 to the right, 5 to the top. Okay, so this is the vector R. Using my triangle law, I continue from the end of R by drawing negative of S. Negative of S will be in the other direction. Okay, so we can count the same way. We are going 2, downwards, and then after that 6 to the left. So we are going downwards now. 2 downwards, 6 to the left. So this is the vector negative S. Start point to the end point will be the vector R minus S. Okay, this is when I use triangle law. Okay. Then in part 2, by looking at the diagram that you have drawn, express the vectors as a column vector. So the vector R is 3, 5. Vector S is 6, 2. Okay, and from the diagram, I see that R minus S is actually going to the left by 3 units, negative 3, going up by 3 units, so positive 3. Okay. So we realize also that even if I do my calculation, like how we do our matrix subtraction, 3 minus 6, it does give us negative 3. 5 minus 2 gives us 3. Okay? So this is true. Seeing from the diagram, this is true if I do our calculation itself. Okay? Then we figure out the magnitudes of the respective vectors. So using our Pythagoras, we get that the magnitude of R and magnitude of S is as such. And magnitude of R minus S, using the vector for R minus S, I get 4.24. So likewise for part 4, we see that the magnitude of the resultant vector is not equals to taking the two individual vectors and subtracting each other. Okay, so the individual vectors or the individual magnitudes, and then we subtract each other, we get a negative value. So therefore, they are not equal. Next, we look at example 9. Right. So let's just do a few of this. Okay. So for part A, right? Okay, we are given this diagram. We want to find out what is the resultant vector equals to. Okay, if we are looking at whether is it A plus B or B minus A minus B. Okay, what exactly is it? So we have to first understand how A and B is actually structured. Okay, so we see that our resultant vector, start point is here, end point is here. Okay, so it doesn't quite follow the triangle law. Okay, if I were to look at this triangle itself, because we know that if I have my two vectors diverging like that, I am not able to do my triangle law at all. Okay, so what we could alternatively think about is that we can use our parallelogram law. So for our vector B, if I were to draw a parallel one upwards, okay, just try to draw the line only without drawing the vector itself. And then after that, my vector A, draw a somewhat parallel one, just a sketch will do. Okay, give us that idea. Right? We see that start point here, end point here. Okay, I'm going to expect my direction from here to here to be the same as B itself. And then from this point to the bottom over here, it is in the reverse direction of A. So that means that this vector is negative A. So if I just focus on looking at this triangle, okay, I'm looking at a B minus A, right? So I'm actually not quite using my parallelogram law, but I'm just trying to shift the lines upwards so that I can use of the space here, okay, to understand the vector movement. So this is a vector B minus A. Okay. So my A and B here is just to tell me how the vector is like. Right? Let's just do one last one, part B, before we continue after the holidays. So in this case, we have the resultant vector moving like this. Start point here, end point here. Not consistent with how our A and B is drawn as well. So likewise, we just draw parallel lines, okay, from B connecting upwards, A around here. Okay. Start point is here. So that means that I need to move up in the same direction as A. And then I need to move left, which is the opposite direction of B. So that's negative B. Therefore, in this case, it is a minus B. Okay. I'll just end here today. After the term break, we come back and continue with this topic. Okay, I will say the main part of it, we have not quite reached it yet. Okay, the main problems that we want to tackle is towards the end. Right? Yeah.